In this chapter, we are going to discuss ideal gases and Dalton law and kinetic theory of gases and Graham's laws and the real gases and liquid state related we are going to discuss in this part. First, we are going gases laws first. Okay. So we have a set of gases laws are there. What is the first gases law? Boyle's law. We know that volume is inversely proportional to pressure, and when you are removing the constant, some constant will become, and taking K1 into P. So PV will be constant will become. So we use formula P1 V1 equal to P2 V2. And also secondly, you can use pressure is directly proportional to density is also at a given temperature for a given amount of substance. They are also same at given temperature for a given amount of substance. So basically, Boyle's law, volume is inversely proportional to pressure. And when you are doing the problem, P1 V1 equal to P2 V2 we are using, or one more, pressure is directly proportional to density. These are formulas we can use. And we know that PV is equal to constant, so the graph you will get like this. Okay, parabola you will get. Is a different temperature you are getting, like T1 and T2 and T3 means T1 is greater than T2 and T3. Okay, so PV is constant. So for this one we are applying the log P is equal to minus log V plus log K. Okay, so this is the graph you will get. Y is equal to mx minus mx plus c. So you will get y is equal to minus mx plus c type graph. Okay, and when you're taking a v versus 1 by p, you'll get the straight line like this. Will give you like y is equal to mx type of graph. Okay, this is Boyle's law related. The second one is a Charles law. According to Charles law, if you increase 1 degree Celsius at 0 degree is Celsius, then volume increases V by 273. Okay, so if you increase the temperature at 0 Kelvin, we are starting, we are increasing 1 degree Celsius, then volume will be increases by V by 273 tons. So that we are using the formula, volume is directly proportional to the temperature and at given pressure and amount of substance. So V1 by V2 is equal to T1 by T2. We are using the formula for doing the problems. Here also can keep constant some K2 into T. So this is also y is equal to mx plus c. Vt you are taking is like this will become. Suppose you are taking both sides log t plus log k2. This is like y is equal to mx plus c. So you will get the graph. Okay, like this. And this is the log p and this is the log. Okay, so the angle will be around 45 it becomes. Why? Because here 1 will be the slope, so 40 theta will be 45 you will get it. So these kind of graphs you will get it for Charles law. Okay, and the next one, we have Wilcox law. So according to this one, pressure is directly proportional to absolute temperature. So you will get at what conditions this one will be applicable? At given volume and amount of substance. So P1 by T1 is equal to P2 by T2. We are using formula. And same way P is equal to some constant K3 into T. So this is also Y is equal to mx type of graphs. So P versus T means you will get the straight line. And next one, if you are applying the log, same you will get it. Log P versus log T, you will get the graph like this. Okay. Similar to this one. This is a Gay-Lussac law. And fourth one, Avogadro's law. Avogadro's law. According to this one, volume is directly proportional to n. Volume is directly proportional to n. So at given temperature and pressure, so V1 by V2 is equal to N1 by N2. Okay. So this is another gases law. So these four gases laws are there. We have first one is our Boyle's law, next Charles law, Gay-Lussac law, and Avogadro's law. Okay. So combining all these gas laws, we get ideal gas equation. Okay. So ideal gas equation is what? Ideal gas equation. So that is that PV is equal to nRT we are taking as the ideal gas equation. It has different forms. So this is the first form, and PV is equal to weight by molar weight into RT. It is the second form. Okay. And third important one, if you are bringing this volume this side and this molecular weight this side, PM, weight by volume will be given the density dRT. So this is very important to find the molecular masses of unknown gases. PM is equal to dRT. And you can also use constant Kv is equal to R by Na, and we know that N is equal to N by Na. So using that, you can get another expression PV is equal to N Kv. Here Kv is a Boltzmann constant. So there is another expression we will get for ideal gas equation. Okay. So what is the significance of R here? R is equal generally PV by RT and T. If you have N is equal to 1, then R will be given PV by T. So this is the work done or energy per temperature. Okay. So for 1 mole of gas, what is the energy per temperature will be given by R. Okay. And suppose we can also derive other real gas, ideal gas equations like gases laws by using PV is equal to nRT. PV is equal to nRT. Suppose N is constant, R is constant, we get P1 V1 equal to P2 V2. So like that we can able to derive gases laws by using the ideal gas equation. Okay. Suppose only N is constant, only N will be constant, then what happens? PV is equal to nRT. R always constant, N is constant. So PV by T is equal to constant. Then P1 V1 by T1 equal to P2 V2 by T2. So only number of moles of substance is constant, we use this one. Okay. And they will give sometimes open system. Open system case, what will be constant will be there is pressure and volume will be constant we can take. In that case N1 T1 equal to N2 T2. Here one important model question is coming. So one student start doing the experiment and he forgot to keep the gap. Some gases escape out. So after he realized, he kept the cap properly, but until that some gases escape out and temperature increased. In that case, how much gas escape out? That we can able to find by using that. That will be generally given by N1 minus N2 by N1. That will be T2 minus T1 by T2. So this will give you the information about the which one? T2. How much gas will be escape out. So this is the open system related. You can use this formula. And sometimes asking payload. What is the payload? how much weight taken by balloon to the up, that is called as the payload. Payload we can find by using the formula, this mass of air displaced minus mass of balloon plus mass of gas. By using this formula, we can able to find the payload. So mass of air displaced you can find by using density into volume. Okay, how to find a volume? Volume of the balloon is 4 by 3 pi r cube. Okay, so volume you can find, and density they will give. So density into volume will be given, mass of air displaced. Mass of balloon will be given in the question, and mass of gas we can use PV is equal weight by molar weight into RT. So we can find by using other information. So after knowing all the information, you can substitute in the formula, you will get a payload. Okay. So these are the concepts. Initially we will get to know that gases laws and ideal gas equation, open system, payload. These terms we can now study. And next we will go through the Dalton law. This Dalton law is applicable only for non-reacting gases. Only applicable for non-reacting gases. It is not applicable for reacting gases. Okay, suppose if you take in Dalton law. Okay, so if you are taking non-reacting gases like systems, helium and carbon dioxide, or O2 and N2 at room temperature, normal temperature, and you are taking carbon monoxide, hydrogen. So like this kind of non-reacting gases, it will be useful like water and nitrogen. Okay, but if you taking this one, ammonia and HCl, so they react each other and form ammonium chloride. So this will be not applicable for this set of mixture. Dalton law will be not applicable. Similarly, you are taking H2Cl2 also. This one, this law is not applicable. First thing they will ask question: which of the following set of gases Dalton law is not applicable? So these reacting gases, it will be not applicable. Here two important formulas are there for this Dalton law. One is the total pressure. P total is equal to sum of the partial pressures at given volume and temperature. Okay. Total pressure is equal to sum of the partial pressures of the gas. What is meant by partial pressure? That individual pressure of gas in a mixture, it is called as the partial pressure. And second, the partial pressure of any gas is directly proportional to mole fraction. This partial pressure is equal to P total into mole fraction. So this is the another formula we are using. Okay. This application, Dalton law applications will be used in collecting the gases over water surface. Suppose you are collecting gases over water surface, then what happens? The total pressure will be the P wet, that is equal to P dry gas and P water. So the total pressure exerted by the wet gas is equal to dry gas plus water. This pressure exerted by this one is called as the aqueous tension. This is constant at given temperature. Aqueous tension is constant at given temperature. So P wet is equal to P dry plus aqueous tension. Now we want dry gas related pressure means P wet minus aqueous tension. Okay. So like that we can apply the Dalton law. So where Dalton law is applicable and what are the important formulas related to that and applications. Okay. Will be useful for Dalton. Next one, we are discussing about which one? Kinetic theory of gases. Kinetic theory of gases. Okay. Kinetic theory of gases. This is a simple one. So what are the statements will be there? I will roughly explain. First, the gas is made up with the small particles, atoms or molecules. Okay. Between the atoms and molecules, there is no force of attraction between them. Okay. There is no force of attraction between the particles. And these particles are very, very small compared to the volume of the container or compared to the distance between the particles. So when you compare to distance between the particle or volume of the particle, the size of the particles are very small, so neglected. So the particle size will be neglected. Volume of the gas particles are neglected. That is the second point. So first point, we are seeing gas is made up of the atoms and molecules. There is no force of attraction between them, and they have negligible volume will be present. Okay, this gas particle move randomly, but they will follow which path? Linear path they will follow. So they will move randomly in a linear path. Okay, so when they move randomly, what happens? They collide with each other and collide with the walls of the container, and they are collide with each other. Okay, and these collisions between these particles will be perfectly elastic. There is no change in energy, there is no change in momentum, but these collisions with the particles with the walls of the container will be exert pressure. So the pressure exerted by the gas is due to the collisions made by these particles when striking the wall. Okay, the pressure is directly proportional to number of particles strike the wall per unit area, unit time. Okay, and another important point, this each particle have some energy, each particle have some kinetic energy, and the average kinetic energy of the particles remains constant. Okay, average kinetic energy remains constant at given temperature, and it directly proportional to absolute temperature. There is another important one. And the particles are moving, so there is no effect of gravity on the movement of particles. So this kinetic theory of gases. Here what is the formulas you have to remember? Here PV is equal to 1 by 3 mn c square. Here m is the mass of the one particle, number of particles, and c is the RMS speed. Okay, and second formula is the average kinetic energy is equal 3 by 2 nRT. Okay, and this one kinetic energy 1 by kinetic energy 2 is equal to n1 p1 by n2 t2. If it is a temperature constant, n1 by n2. If number of moles remains constant, t1 by t2. Okay, so these are kinetic theory of gases related and kinetic energy related formulas you have to keep in. Next one, what we have, Maxwell distribution curves. Okay, so he tried to give the graph. So number of particle by fraction of particles having particular speed is taken consideration. At given temperature means you will get the graph like this. Okay, you will get the three types of velocity. Okay, u most probable, u average, and u RMS, like that you are getting the velocity. At particular temperature, this u RMS will be more, u average is more probable. And suppose I am taking different temperatures. This is a T1 temperature and T2 temperature. I increase the temperature. So when we are increasing the temperature, this speed of the particles will be increases, and the fraction of molecules will be have high speeds will be there, so that sided particles will be moved. See, compared to here, this is the URMS taking is this particular URMS you are taking is the particular temperature will be increases, the RMS speed or most probable speed or one more average speed will be decreases. Okay, and now here when you compare these two graphs, what happens? T2 is greater than T1 will be there, and here the fraction of molecules having the average speed or RMS speed like that are decreasing, but the speed will be increasing. Okay, speed will be normally C2 is greater than C1 will be there. Okay, speed will be more, will be increases. So that is another one. And here fraction of molecules by N you are taking. Now different gases I am taking. Okay, this is a gas 1A, the gas B. If more the speed we are taking, so gas A have less speed means molecular weight if you are taking, okay, A is greater than B means speed will be what happens? B greater than A will become. So like that will be affected, will be there. Okay, so what you can learn mainly, so fraction of molecules having a different speed at particular temperature, it is this one, 3 types, most probable, average, RMS. Okay, the fraction of molecules versus speed we are taking different temperature, we are taking particular RMS speed or average speed having particles will be decreases, but if you are taking speed will be increases particles. So T2 is greater than T1 means speed of the particles will be greater than speed of the particle at T1 temperature. Different gases will be having more molecular weight is there means the gas will be moved slowly and other will be moved fastly. Okay. These are Maxwell distribution curves we have to remember. Next one, Graham's law of diffusion. What is the diffusion? Generally, the homogeneous mixing of gases is called as the diffusion. Effusion is from the small orifice or small hole, the gas is escaping out is called as the effusion. So diffusion and effusion related things will be given by Graham's law. Okay. So Graham's law, what they are? Graham's law is, if you are taking rate of diffusion or rate of effusion is inversely proportional to molecular weight at given pressure and temperature, or rate of diffusion is inversely proportional to density, square root of density at given pressure and temperature. These are basic statements for Graham's law of diffusion. Okay, using that, and also we know that rate of diffusion is volume of gas diffused by time. Okay, there is also common we can use. So we will get R1 by R2 is equal to square root M2 by M1, that is equal to square root of D2 by D1, that is equal to vapor density given means VD2 by VD1, that is equal to what we are getting, V1 by V2 into T2 by T2. So this is at given temperature and pressure. Okay. Now, if in one case pressure is constant, or other case if temperature is constant, so what happens? Okay, pressure is constant means R1 by R2 will be is under what? Square root of M2 by M1 into, it will be T1 by T2. Okay. And also if T is constant means R1 by R2 is equal to P1 by P2 into square root of M2 by M1. Or also you can use R1 by R2, P directly proportional to N means N1 by N2 square root of M2 by M1. So this formula also we can use. This Graham's law of diffusion related formulas. Okay. Next, this same formulas will be applicable for effusion related also. So rate of diffusion inversely proportional to molar mass of the gas at given pressure and temperature, or inversely proportional to square root of density at given pressure and temperature. Okay. So these are the formulas we can use for Graham's law of diffusion. Okay. Now, what concepts we have completed? Kinetic theory of gases, kinetic energy, Maxwell diffusion, grams. And also we can here discuss different velocities will be there. So U, most probable velocity, is equal to, what is the formula will be there? 2 RT by 2 RT by M, you will get it, 2 RT by M. And the next one, PV is equal to nRT, you can also use 2 PV by M. And if density related, 2 PV by T. Okay, so this we can use most probable speed, the gas particles case, the possible most probable speed will be taken here. And next one, average speed is equal to 8 RT by pi m we are using. And the same way, U RMS speed will be used 3 RT by pi we are using. So what is the ratio for this one? U most probable, U average, U RMS is equal to 1 is to 1.128 is to 1.224. Okay. And same way you are taking U RMS first, U average and U most probable you are taking. Then it will becomes 1 is to 0.921 is to 0.816. You will get it. This is a ratio. So one of the gas, suppose anyone most probable speed is given, they are asking RMS means you can use this formula 1 by 1.1. Okay. So then you already one means other you can able to find out. So these are gases, molecular speeds of the gases. Okay. And any molecular speed you are taking, any molecular speed that is directly proportional to square root of temperature and directly inversely proportional to square root of molecular weight. So U directly proportional to temperature by molecular weight. Okay. So this is any molecular weight related, any molecular speeds related to this. Okay. And this part is over. Next one will be have real gases. So what we are studying, the ideal gases. Okay, so there is no ideal gas exist, all will be real gases there. So real gases behave like ideal gas in particular conditions. What are the conditions? It will be high temperature and low pressure. So high temperature, low pressure case, real gases behave like ideal gas. Remaining case, we will exist only, we have only real gases. So how? Why they are different, differ from the ideal behavior? How they are differing? How we know that they are deviating from ideal behavior? So in that case, suppose we are taking the compressibility factor PV, this one, and versus pressure we are taking. Here Ez is a compressibility factor, that is the PV by nRT, or V real gas by V ideal gas. Okay. So compressibility factor, we know that ideal gas means it should be 1. So we are expecting 1. But hydrogen you will get like this, and helium you will get like this, CH4 you will get like this, CO2 you are getting like this. So no gas is perfectly following the ideal gas equation at all temperature and pressure conditions. But low pressures, it will be showing that what ideal behavior, and this below it is coming means it is the Ez will be less than 1. Here above is coming means Z is greater than 1. When Ez is less than 1, here attractions will be dominant. So this kind of gases easily we can convert into liquids. Ez greater than 1 means here repulsions will be dominant. Which will be dominant? Repulsions are dominating. We cannot easily convert into liquids that one. Okay, so these deviations are coming. So the basic problem why they are deviating is when you apply the kinetic theory of gases, two major violations it is found. One is first, we are neglecting the force of attraction between the particles, and we are neglecting the size of the particles. So these two will be major problems and which will be causing the deviation from ideal behavior. To avoid that one, van der Waals equation is given. Van der Waals equation is given. So the pressure correction they have done, okay, an square by v square, and same way volume correction they have done is equal to nRT. They given this by correcting pressure and volume, they given ideal gas van der Waals gas equation. And in this gas equation case, so we have A is a van der Waals constant and B is a van der Waals constant. Okay, for us important, what is the units for A and B? For units for when two things are added, they must have same units. So that's why these units will become ATM, liter square, mole power minus 2. And this should also have same units. So this is volume, is liter, mole power minus 2. Okay, so these are the A and B units. What is the information is given by A? A measures the force of attractions. Okay, and B measures the size related. Okay, and incompressible volume. Incompressible volume. So A measures the force of attraction and B measures the size of the particles related and incompressible volume related. It is giving the information. Okay, and now these real gases are there. Okay, how we can able to convert into liquids? Okay, how we can able to convert into liquids? Generally, when you are taking the pressures versus volume. Okay, I am compressing the gas. What happens compressing? Some point I am started compressing the gas. It follows the Boyle's law. Pressure will be increases, volume will be decreases. After a particular point, it start converting to liquid. Okay, and after converting to liquid, so this point A and B point will be converted into liquid, and the C point it is converted completely into liquid. After that, how much compressed? The pressure will be increases, but volume remains constant. Similarly, this is a T1 temperature. We are increasing the temperature, the horizontal will be decreases, and finally it will be come to the 1 point. Okay, so this will be gas state, air equilibrium, and it is a liquid state. Now we have only gas state only. After this point, only gas state. How much you are compressing after particular temperature? You cannot convert gas into liquid. Okay, so this particular temperature at which above which gases cannot be converted into liquids by applying the pressure only, then it is called as a critical temperature. The corresponding volume is a critical volume and corresponding will be critical pressure. Okay, so whenever you are liquefying, what you have to do? We have to increase pressure and decrease temperature. That we have to do. Here particular temperature we are keeping, and we how much compressing, that will be cannot be converted into liquid. So this is, you want to liquefy, increase pressure, decrease the temperature. Okay, and this we have known. Now what is the values for this expression for TC and VC and VC? VC is equal to 3T and TC is equal to A by 27 RB square. And the next one you have TC, right? A by 27. Okay, 8 A by 27 will be covered. R this square will be covered. So VC is equal to 3T, PC is equal to A by 27 B square, and TC will be 8A by 27 R. This will be come, and here other than this is the critical temperature we are studying. Same way Boyle's temperature will be there, that is the A by RB. Inversion temperature will be there, 2A by RB. So what is the Boyle's temperature? That will be important one. Okay, so at a particular temperature, particular temperature, these real gases behave like ideal gases over one range of pressure. Over a range of pressure, that will be real gases behave like ideal gases. Then it is called as the Boyle's temperature. What is the inversion temperature? It is comes in Joule-Thomson effect. So it will be inversion temperature where cooling will be taken when you are doing the expansion. Okay, so that is a inversion temperature. So critical temperature, Boyle's temperature, inversion temperature expressions we got. So that is the liquefaction and critical constant van der Waals equation and this one. Okay, so these are mainly for us states of matter related or gas state related. And the next one, what we have, liquid state. Liquid state. So liquid state is surface tension we have. So basically what kind of questions will be asked? What is the units for that one? Newton per meter. So the force acting on for a unit length perpendicular to the surface, it called as a surface tension. So Newton per meter will be the units. If your temperature increases, surface tension will be decreases. Pressure increases, surface tension will be increases. These 2 points will be important. If you have intramolecular forces, intermolecular forces increases means the surface tension also will be increases. Okay. These are the main points you have to keep in surface tension. And same viscosity related. Okay. So here the coefficient will be Newton, that will be have units Newton meter power minus 2 second. Okay. And here also viscosity, temperature increases, viscosity will be decreases, and pressure increases, viscosity will be increases. Same intermolecular forces increases, viscosity will be increases. This is the another point related to viscosity. And we already know that vapor pressure. Vapor pressure means, okay, when liquid and gas at equilibrium will be equilibrium, the pressure exerted by the vapor is called as a vapor pressure. And this vapor pressure, when it is reaching 1 atm pressure, atmospheric pressure, or 1 bar pressure. Okay, so this vapor pressure is equal to 1 bar or 1 atm. So 1 bar is the standard boiling point we are calling, and this is the normal boiling point we are calling. Standard boiling point, normal boiling point. This is around 99.60. This is 100 degrees Celsius. Okay, so these are vapor pressure related terms. Okay, so this is about states of matter. Okay, so we discussed gases laws, ideal gas equations, open system, payload, Dalton law, kinetic theory of gases, kinetic energy, Maxwell distribution curves, Graham's law, real gases case, compressibility factor, van der Waals equation, liquefaction, critical constant. Liquid state, briefly, that what is the units, what happened with the temperature and pressure, and intramolecular forces. What is the normal boiling point and standard boiling point, vapor pressure. These are the terms we have discussed. Okay, so this is about the states of matter.